Hello and welcome to the Florida Water Resources Monitoring Council webinar. I'm Dan Doherty with the Balmoral Group. I serve as chairperson of the Water Council, and today we have two really interesting talks as part of this webinar. The first from Scott Prinos, who's talking about hydrologic analysis and mapper resource it's a really helpful resource, and the R package behind it for analyzing and visualizing hydrologic data. And we'll also hear from Matt Petkewich from USGS at the South Atlantic Water Science Center, and he will be talking about the expansion and upgrade of the Coastal Salinity Index. When Scott gets started here, the recording was cut off right at the beginning, so we're missing his intro, so we will just get right into it with Scott Prinos.
EP had pursued trying to create something like the USGS Groundwater Watch, but with data from the water district. So this is the USGS Groundwater website, and you can see that there's a map and a whole bunch of symbols on the map, and everything breaks down into percentile classes. So green would be basically normal water levels. So from 25 to 75% of the time, the water levels are found at that level. Lower water levels are in the dark brownish red or red, and higher water levels are found in the light blue or dark blue symbols. The symbol shapes in this case were used just to differentiate between the types of water that were, or the types of measurements that each one was. Since that time, USGS has developed a new website, the Water Level and Salinity Analysis Mapper website. That takes advantage of symbol shapes to add to what Groundwater Watch showed. And this one shows you the trend of water level through time. You can select a series of options on the left-hand side. The menu you can select from. You can select different types of measurements, semi-annual, annual, quarterly, bi-monthly. You can also look at different trend periods, such as a 5-year trend or a 20-year trend. You could look at the change in the last week or the change in the last month. The map will update automatically. So this allows you to look at many different kinds of changes beyond what Groundwater Watch used to show. The Water Level and Salinity Analysis Mapper provides analyses that answer the following questions. Where are groundwater levels high, low, or normal relative to historic data? Are there long-term trends in water levels? If so, in which areas and what aquifers? Did water level increase or decrease during the last week or month? Where is salinity in a given aquifer increasing, decreasing, or staying the same? What is the current extent of saltwater intrusion in each aquifer? This website includes features that Groundwater Watch did not. Okay, so here's an example of just the water level analysis. You already saw the map. So what happens is, and again, I'll just describe the symbols. The upward pointing arrows is an upward trend in water levels. Downward pointing arrows would be downward trends in water levels. And a square would be insufficient data, and a circle would be no significant trend. So if you were to click on any one of the sites, you would be able to see the site name and a link to a page, which I'll talk about in a minute. You'll see the value of the last water level, the date of the last water level, the change in the last week, the change in the last month, the 5-year trend, the 20-year trend, and the composite trend. So that information is just in a little pop-up. Then if you were to click on a link, it will take you to a page that provides you with graphs and tables for that site. Among the graphs that are shown is a weekly breakdown of the frequency analysis of historic water levels. So again, red are lower water levels, green is the normal range from the 25th to 75th percentile, and the blues are higher water levels. You can see that the current data, the squiggly little line, in black and red near the top of the graph, that's the current data, and it's generally high water levels, okay? The next graph down, looking at the right side, shows a blue shaded area, and that area represents the difference between the minimum and the maximum for each day of the year for the period of record. So those are the lowest and highest water levels ever attained during those days. You can see again that the current data is near the top of that range. That's the black line and the red line. The yellow line represents the of the historic daily values. So why is it near the top end of the range? If you look at the graph at the bottom on the right-hand side, you'll see that for a long time there was a downward trend in water levels, and now for the last 20 years, there's been a statistically significant upward trend in water levels, so that now the water levels are actually a little in the higher end of the range of the historic data. Now, here's an example of the salinity analysis. If you were to look at the salinity tab, which is on the left-hand side of the website, there you have the options of selecting, again, different kinds of sites measured at different frequencies. And you can look at the 5-year trend, the 20-year trend, or a composite trend. The composite trend is a symbol that combines the 5-year and 20-year trend together. So you see a series of arrows on the map, upward pointing arrows in this area for the most part, and a few squares where there's insufficient data for trend analysis. The red upward pointing arrows indicate an upward trend in chlorides, and that the chlorides are 1,000 milligrams per liter or higher. The blue symbols indicate areas where the chloride concentration is 250 milligrams per liter or lower, and the symbol shape again is the trend. The saltwater interface has been moving inland in this area rapidly. So in 2011, the red line on the map shows where the saltwater interface was, and in 2018, the green line shows where the saltwater interface was. So in that period of time, it moved inland a fair amount. If you were to select any site on the map, it allows you to see the date of the value of the last chloride sample, the date of the last chloride sample, the 5-year trend, the 20-year trend, and the composite trend sample. If you click on the link, it will take you to a page that shows you a series of graphs, tables, and other information. And that includes a graph on the upper right-hand side, which is the chloride concentration through time. You can see it's rising quickly in this area. You can see in the middle graph on the right-hand side the specific inductance. And then the bottom graph is the chloride concentration versus specific inductance. So that's kind of a quality assurance graph. If you have something that falls significantly off this line, it may be that there's a bad analysis. So the graph towards the middle below the map shows the result of a series of electromagnetic induction logs that were collected through time. So the y-axis is depth, and the x-axis is bulk conductivity, and the bulk conductivity is increased through time, which is not surprising considering that the chloride concentration is increasing. Although the website currently only shows groundwater levels and groundwater salinity, the same scripts can evaluate other parameters. We can look at stream flow analysis. So instead of groundwater levels or salinity, we can look at flow in rivers or canals or streams. And we can look at trends in the streams. And in this case, there was a 20-year statistically significant increase in flow. And then there's the same analysis that you could do based on your weekly percentiles of the historical data compared to the current water level or current flows, in this case, in the black line and the red line. Specific conductance can be looked at the same way. So this is a continuous specific conductance monitoring gauge in the St. Lucie estuary at Steely Point. And the data, the long-term data, is shown in the lower left-hand corner. And the blue data is the approved data. The red data is not approved yet. That's the provisional data. And you can compare that to the historic breakdown of the percentiles. Okay, we can look at tidally filtered discharge. And that's the graph on the upper left is the long-term period of record graph. Then you have your percentile, your comparison of your current flows, your current discharge to the historical breakdown in percentiles. Then you have the minimum and maximum comparison that you can compare it to. And then you have on the lower right-hand corner, you have the unit value data. So that's the hourly or 15-minute data from the site. We can look at salinity. So I already showed you the graphs of specific inductance. Salinity is just another way of looking at it, other continuous monitoring probe. And so this is salinity in the Spring Creek, near Spring Creek, Florida. And you get the same series of graphs that you can look at for that. You can look at, throughout most of the country, we have a series of gauges that are a combination of gauge height and flow. So you can look at the gauge height, what's the water level in the stream, and you could look at that time. And in this case, at the Little Wabash River in Illinois, there's a statistically significant 20-year upward trend. You can look at the minimum maximum for the period of record for each day of the year, and you can look at your percentile breakdowns versus your current data and your unit value data. So those are the graphs that were part of the website. And the R program language was used to create all these graphs, tables, header files for the water level and salinity analysis mapper. What is the R program language? R is an open source programming language. It has good tools for manipulating data. There are over 10,000 analytical packages in the repository. Each package has many different functions in it. It has good plotting and graphing capabilities. R can be paired with other languages like C, C++, Java, and Python. It is platform independent. It can be used for machine learning operations. R has a large variety of statistical packages available. And R is a constantly evolving programming language. So HASP, for example, is something that the USGS has just added to R that other people can use. So what is HASP? HASP is the hydrologic analysis package that was developed by the USGS based on the scripts for the water level and salinity analysis mapper. So the same scripts that were used to create those graphs that you saw for that website and all the tables and all the information for that website has been turned into a R package that's publicly available. If you were to go to the website, which is shown in the upper left-hand corner at GitHub, you can see the HASP package, and you can access the code there and everything you would need to be able to make the same kind of scripts and charts you see here. So here is a monthly breakdown of the water levels, comparison of the water levels to the monthly water levels to a monthly breakdown of the percentile analysis. And the graph on the lower middle area is the long-term data, with the trends shown, the 20-year trend and the 5-year trend shown as green lines. And the graph on the lower right-hand corner is your comparison of the current data to the minimum and maximum for each day of the year and to the mean, which is the green line is the mean for the, so this, in this case, the data, the current data is comparing pretty closely to the mean. Station info is provided, so it will automatically go in and it will pull the information for a USGS station. And you can get links to the USGS website through some of the scripts that run. Here's some other examples of HASS tables and graphs. So here's the weekly breakdown of the historical data as percentiles versus the current data. Now, in this case, you can see that the black and red line, the approved and the provisional data are well below any of the percentiles that are shown on this graph. You can also see that it's below, in some places, even the minimum for the period of record. Okay, you can also see the chloride from this same well and the 20-year trend and the 5-year trend in chlorides. So it was basically not doing a lot, but recently it's started to increase sharply. And so this plot, the long-term plot of water levels, shows why you're seeing that the current data is well below the other, the percentiles and the minimum maximum comparison. There's just a very sharp downward trend through time in this well. You also have tables of period of record, min, max, and quartiles, and tables with the trends and stats for the chlorides, and many other tables and charts. So I won't go into all of them. So in the end, what could you use this for? Well, HASS currently is USGS hydrologic data. Okay, it takes it and it analyzes it through the hydrologic analysis package, ASP, creates the analytical results that could be put on a server, like what we have for our website, and then analysis and retrieval scripts from the website, pull those tables, charts, and graphs, put them into the hydrologic conditions and trends mapper. And that's what's shown on the current website. But imagine if you took non-USGS hydrologic data, and now that HASS, the hydrologic analysis package, is readily available. You run that on other people's data. You get the analytical results. You put that data on the server. Then you combine the two sets into the analysis and retrieval, through the analysis and retrieval scripts, and put them both on a hydrologic conditions and trends mapper. Then the user, through a hydrologic analysis liaison, HAL, could potentially access the site and get anything they want. And the reason I'm suggesting an AI is that it might make it easier when we start considering every possible kind of data that we could actually look at with these kinds of scripts. The liaison could potentially hand tailor a page so that you're looking at what you want to look at. And that's all I have.
Wow, that was great. Thanks so much, Scott. So anyone with questions, feel free to unmute yourself, or if you have, if your audio is not working, you can type something in the chat. But what questions do we have for Scott?
Hi, this is Rick Copeland, and from Florida DEP, and in our old Salinity work group meetings, we had these kind of presentations, and I just want to let everybody know, from my perspective, if we could get this through the wind, the data eventually gets into wind, and we could use this, I see, potentially. So I see a lot of great potential for it. So don't have a question, it's just a comment.
Thank you.
Scott, I just saw a question in the chat. Are you willing to make these slides available to us as a PDF or something that we could share with the group, or
Yes, I think we
how
can.
do you feel about that?
I don't think there's
Okay.
anything. I'll run it past my supervisor to make sure that there's nothing that they feel is, but most of this stuff is out there already.
Okay. I'll follow up with you about that. Thanks.
I should mention that, you know, talking to Brian Turcott from the South Florida Water Management, he mentioned that they had created scripts to go into the water management database in R and pull the data out. So potentially, if you put that together with modifications of HASP, because again, HASP is designed to reach into the USGS database, so there'd be some modifications that would have to be made to HASP to grab non-USGS data. But really, once you've got the data, then the rest of the package should work fine on it. And it's from what I understand, I didn't create the HASP package. Some other programmers in the USGS did that based on the scripts that I provided. But my understanding from them is it was designed with that in mind, that people could use this on their own data.
Okay, good. That's helpful to know. I had a question, Scott. You showed some examples of, you know, of Illinois and some other like data visualizations from other states. I mean, the map or web link you shared looked like it was for Florida. How many states have the kind of web interface that links to all this data versus the states just having kind of the underlying, you know, HASP that they use for their own purposes? But how many folks have a map or interface?
Yeah, right now, nobody. It's just South Florida. What I've been doing is trying to show other states what they could do. And I've been trying to suggest this as a replacement for Groundwater Watch, which is grandfathering itself. I mean, the scripts behind that, I worked with the person who had created the original scripts for Groundwater Watch. It was based largely on our prototype website that we created for Florida. And so those scripts are pretty old. That was developed around 2000. So they're 20 years old now. And, you know, they're kind of struggling to maintain it because there's been big architectural changes to our database since the time those scripts were written. Ultimately, I created this newer version because the changes to the architecture of the database affected the old prototype that we had developed, and our cooperators were looking for a replacement for that prototype. So, yeah, I've been showing other people. New York has expressed interest in running it on some of their data, you know, but I've been just trying to give demonstrations of what could be done if they would go with this as a replacement. But the bottom line is that I'm trying to make is that, you know, the script doesn't care where it's getting the data from, whether it's Illinois or New York or, you know, Boston, whatever. It will be happy to digest the data and put out the same kind of graph. And we don't have to limit ourselves to just looking at groundwater level or groundwater chloride. We could look at the full hydrologic analysis of, you know, rivers, streams, canals, salinity in rivers and streams. You could look at constituents. You know, just because we design the scripts for chloride doesn't mean you can't run them for other constituents. So that's the kind of direction that I'm looking at.
Can I ask a question? Can you hear me?
Yes.
This is Kelly Young with Volusia County. Is this something you have that's connected with Aquarius? The program I was thinking was something that USGS used for their data database.
We use Aquarius. Basically, Aquarius is the interface that we use to process the data when we're working on it, when we're applying corrections to the data. and then it goes into the INWIS database, and then there's a script that you may already be for a package that you may already be familiar with, where it's my mind right off. But it basically takes the data. It's not INWIS web. It takes the data and it puts it out on the web. In that really, if you write a complex URL, you can get at the data directly. So the USGS data retrieval program takes advantage of that script and pulls the data out of our database. And so it's taking advantage of another USGS package that is supported. So we use the package you mentioned, Aquarius, to process the data, and then it gets put online, and then this script takes the data from there.
Okay, thank you.
There's a question in the chat. I'm going to read to you here, Scott. Is HAF, as shown here, the same set of tools that create the surface water graphs in the new USGS surface hydro tools, the Water Watch toolkit? Is that the same thing here?
No, it's a different set of graphs.
Gotcha.
Yeah, one of the things that we do that, you know, some of the other places aren't as interested in is breaking the frequency analysis down by week. When we first created the prototype to Groundwater Watch, we soon realized that all the little dots you see on the map, at the end of the month, they suddenly change color. That was because on the last day of the month, it was being compared to that month. Next day of the month, it's being compared to the next month. And there's a cycle of water levels throughout the year. So it's just a change in the comparison that happens rather abruptly and would cause the dots to suddenly change color on the map. So by breaking it down by week, it reduced that tremendously. And so you had a smoother transition through time so that you weren't suddenly seeing something go from high water or apparent high water levels to apparent low water levels overnight.
I see. Makes sense. So there's another question from the chat. Are the NWIS data stored in a relational database?
They're currently stored in Aquarius, which is a version of a relational database. So basically, the data come in, they're stored in a database, we process the data through Aquarius. Aquarius then stores that data in the official USGS database, which is a relational database. Then a series of scripts come, take that data and put it out through INWIS Web, and they also put it out through, now I remember the name of that other service, it's called Web Services. So it also puts it out to Web Services. And from there, the public can access the data either through INWIS or Web Services. This script takes it from Web Services and creates all the plots and charts.
How to get people back to child care and better health. I've told several of you over the last several weeks.
Okay, great. Thanks, Scott. I'm hearing someone else talking, so if you could mute your phone or your computer or whatever. Any last call? One more question for Scott, if someone has one. Okay, awesome. Well, thank you so much, Scott. This was fascinating and super helpful. So thanks. And I am going to switch it over to Matt. While I'm doing that, I'm going to mute everyone. So we're going to hear we're going to hear from Matt Petkewich with USGS. I'm going to mute everyone. So Matt, just be prepared to unmute yourself. And I'm going to hand the screen over to you. Okay, Matt, can you chime in? I would just want to make sure I can hear you. Matt, can you? Okay, Matt, try. We can't hear you yet. Can you try to talk again?
Can you hear me?
Yes, we can hear you.
Okay, I think I had two icons up there, so maybe you grabbed the wrong one.
I maybe did.
Okay. Is my screen up?
Not yet. Is anyone else seeing Matt's screen? Let me.
No.
Let me try again.
Okay.
Okay, now we're seeing it. We're seeing your desktop. Okay, there it is.
Okay, full screen. Everything looks all right?
Yep, I hear you well, and I see a full screen.
All right, great. Yep. Need to get through the technical issues first. But,
Yep.
All right, very good. Good afternoon, and thanks for having me. I'm Matt Petkewich. I'm a hydrologist with the U.S. Geological Survey in South Atlantic Water Science Center, located in Columbia, South Carolina. I've been with the USGS for 29 years and participated in a variety of water quality investigations related to surface and groundwater resources in South Carolina and even some in Florida. I'm a project member of the Everglades Depth Estimation Network, and I've inherited the Coastal Salinity Index project from its creator, Paul Conrad, who worked with me in the USGS in South Carolina, and also he was a member of the Eden project. Funding for the Coastal Salinity Index has come from the USGS, NOAA's National Integrated Drought Information System, and also the Regional Integrated Sciences and Assessment partners. A quick overview of what I'll cover during today's presentation is what is the Coastal Salinity Index? I'll describe new products and resources that were published in 2019, and I'll briefly discuss our current project, which is in this year, 2020. So, common drought indices use many inputs for classifying drought. These include precipitation, stream flow, evaporation, and soil moisture conditions. However, these drought indices do not capture the changing salinity dynamics that affect the coast during drought. So droughts and floods affect the location of the freshwater-saltwater interface in coastal estuaries and rivers. This graphic shows what would happen if you get a lot of river flow towards the ocean. It'll push the freshwater-saltwater interface towards the ocean. Or if you have the freshwater-saltwater interface will move inland during lower river flows, such as during drought or during high tides. Salinity and reduced freshwater availability is a key stressor during drought. And the concept was the focus of the National Integrated Drought Information System, Coastal Carolina's Drought Early Warning System. This group asked, can there a unique index be used to develop to characterize coastal drought? To address these issues, the USGS created the Coastal Salinity Index through the quantitative analysis of long-term salinity records. The Coastal Salinity Index uses an approach similar to the standardized precipitation index. Instead of using precipitation, The Coastal Salinity Index shows the probability of recording a given amount of salinity. Monthly mean salinity values are fit to a gamma distribution and normalized with a mean of 0 and a standard deviation of 1. Index values are standard deviations from the normalized mean value. So index value of 0 indicates historic mean salinity. Negative values and positive values represent saline and freshwater conditions, respectively. So here's the table at the bottom showing the classifications of the Coastal Salinity Index, the description, the icon, color, range, and threshold values. The CD stands for coastal drought and represent salinity conditions, anywhere from abnormal salinity conditions to exceptional salinity conditions in increasing red concentrations. And these range from a minus 0.5 to greater than -2 or lower than -2. For coastal wet or freshwater conditions, they range from CW0 to CW4, from 0.5 to +2, and go from abnormal freshwater conditions to exceptional freshwater conditions. The standardized precipitation index threshold values were used to develop these thresholds and designations. This was developed and published in a Bulletin of American Meteorological Society paper in 2017 by Conrads and Darby. The Coastal Salinity Index can be computed for multiple time intervals to characterize short, medium, or long-term conditions. Here we have 3 graphs showing the Coastal Salinity Index, 1 month CSI graph on the bottom, 12 months in the center, and 24 months at the top. So we have along the y-axis is the average salinity concentration in parts per thousand. Across the bottom is time, and the black line across the center of the graph, that is the rolling salinity value over time. This is a 1 month average salinity over time. The colored background is the Coastal Salinity Index designation. So when you see high salinity concentrations, then that's where you see the dark red color codes in the background. And when you see low salinity concentrations, that's when you'll see the dark blue. And so the 1 month Coastal Salinity Index, you see it's pretty flashy over time. This is the period of record from 1995 to the present. If you look at a 12-month interval, the line is an average 12-month rolling average of salinity over time. You see it's kind of muffled a little bit, and it becomes even more smeared or muffled for 24 months. So in 2019, our CSI team completed an investigation that resulted in 4 main products. The first one was the Coastal Salinity Index R package. This is located on GitHub and is available for folks to go and grab and use to calculate your own Coastal Salinity Index values for your station of your interest. We also calculated historic Coastal Salinity Index values and graphs along the Gulf of Mexico and Southeast Atlantic coast. We did this for 96 historic sites, representing a period record from early 90s or 80s to 2019. These are located in the USGS Science-Based Catalog. We also created 2 real-time Coastal Salinity Index web pages. One was in the South Atlantic Water Science Center and shows 17 real-time salinity gauges for North Carolina, South Carolina, and Georgia. A second real-time CSI webpage is the USGS Coastal Everglades Depth Estimation Network, where we have 12 stations showing real-time Coastal Salinity Index graphs. These resources and products were published in an open file report, USGS open file report, published in 2019. In the appendix of this report is a user's guide, which will show you how to use the Coastal Salinity Index and how to interpret the different graphs. So this year, we received funding, our CSI team received funding from the USGS Community for Data Integration. And this was a short-term project from May to ending this month or early next month. A small pot of money to increase our footprint for the Coastal Salinity Index. So we had 3 objectives. First, we wanted to identify and integrate salinity data sets into our South Atlantic Water Science Center CSI website. To do this, we needed continuous data, we needed real-time data, and easy access and for grabbing that data, processing it with our R scripts, and uploading it to our website. So because of the short time frame, we focused on 3 agencies: the USGS salinity data sets from our NWIS network. We looked at the National Park Service in the Everglades National Park. There's about 30 gauges that we're grabbing from there. And the National Estuarine Research Reserve stations, we're using about 30 of their real-time gauges that we're going to incorporate. Our second objective was to enhance the website and user interface to accommodate these new CSIs. In doing so, we're going to expand the map from Maine to Texas and Puerto Rico. We're also going to include dynamic interactive graphs of the Coastal Salinity Index, salinity, temperature, and gauge height, user-friendly tabular data, and we're going to provide links to the originating agency websites for the raw data. We don't want to serve up the raw data. We don't want to be the provider to that. We just want to provide the results of the Coastal Salinity Index. Finally, we are also going to further develop some of our CSI R scripts for use in ecological analysis. And the one that we're doing is a case study synthesizing data across spatial and temporal scales and see how that works out. We're going to publish a journal article describing the results next year. So we'll do a quick walkthrough of the Coastal Salinity Index website. This is the one developed for the South Atlantic Water Science Center, USGS. It's still a work in progress. We haven't completed it yet, but I'll show you what has been completed so far. Here's the home page, and it's real-time salinity data from Maine to Texas and also in Puerto Rico. We have the three different agencies. We have USGS shown in circles. The squares are the National Estuarine Research Reserves, and the triangles located in South Florida are the National Park Service gauges. We show the CSI table here with the descriptions and threshold values and the colors representing the different gauges that are on the map. You can choose in this explanation box the time interval of interest. If you're interested in a 1-month CSI, that's what we're showing now. If you're interested in a 12-month CSI, you can change that and it'll change the color of the different gauges. If you dig a little further, you can zoom in on this landing page, our home page, and you can click on a site of interest, and up will pop a window, and it'll give you the station name, the agency that the station comes from, the current CSI interval for the time interval of choice. So right now it's a 1-month CSI value of 1.11. You also have links to view the station page. That would be it'll take you to the landing page for that gauge. So this one's a NEARS gauge, so it'll take you to the NEARS gauge page for that one. You can download the input data that was used to calculate the Coastal Salinity Index, the output data, and also view graphs, the Coastal Salinity Index graphs for that gauge. So these links are also located in the table, located beneath the map. And here's a quick look at that table. So it lists station ID, name, agency, state, this current CSI value for your interval of choice. So now we're showing the 6-month interval. And then all the links for the station page, download data, and view graphs are available there. These headers are sortable and searchable. So you can sort by station name or state if you're interested. You could also search if you're interested in looking at the Waccamaw River in South Carolina. You start typing Waccamaw and it'll pull that gauge up. On the pop-up or the table, you select monthly graphs. And if you go to monthly graphs, something will pop up like this, showing the 1-month Coastal Salinity Index for that gauge, 2-month, 3-month, all the way down. You can scroll down to the 24-month graph. That's what the monthly graphs tab does. We're going to jump over the About CSI page real quick and go to the additional data page. The additional data page is additional real-time data that you can look at in graphs, just kind of evaluate your CSI gauge of interest. So here's what it would look like if you choose salinity and average salinity and 7-day time interval. It's going to show you the color codes for those gauges that are on the map. And to dig a little further, you can click on the data source, and you can choose salinity, water temperature, or gauge height. You can also look at average salinity, water, or gauge height, or you could look at the change in salinity, water, and gauge height, depending on the time interval of your choice. Here's the time intervals that you can choose: 7, 14, 1 month, 2 months, 3 months. So some folks might be interested in a 1 month change in salinity, and so if you choose that, that's what will be populated on the map and shown for all the gauges on the map. If you click on the icon, here's a 7-day salinity for this gauge. You get all the agency information, the current average for the salinity for 7 days. And then you can access, once again, the input data. You could view the you could view the graph of a 7-day salinity graph, a 30-day moving window graph, and also the stacked CSI graphs, which I did not go over, but they're available on this pop-up. Here's an example of water temperature change, something similar to what Scott Prinos showed earlier. These are arrows showing this 7-day change for water temperature. So you can see for the past 7 days, the temperature in South Carolina has dropped at all these water temperature gauges. Here we have 2 of the graphs that you can select when you click on an icon. Up top, we have the salinity, a 7-day average salinity. The dark trace in the back is a purplish color, is the daily salinity over a 3-year period, and the green is the 7-day rolling average salinity value over time. You can choose your gauge of interest and your parameter of interest to view that. At the bottom, we have a 30-day moving window average graph. It's shown for the last 3 years period of record. Scott showed something similar to this. We're showing 3 years instead of just 1 year to see how it's changed over the 3 years. So the black line is the 30-day moving average salinity value. The gray line, which doesn't show up greatly here, but the gray line is the daily salinity values. Yellow line is the historic monthly average salinity value for each month. And the bins represent the different percentile bins, the salinity. You know, the dark brown is less than 10%. The lighter brown is 10 to 25%. The green is the more normal. It's the 25 to 75%. The light blue, 75% to 90%, and the dark blue is greater than 90% to the maximum. So a quick overview of the About the CSI page. This is kind of a data information page. You know, it describes the motivation of why we developed the Coastal Salinity Index, the methods we used, CSI classifications description. It describes how to read a stacked graph, a CSI stacked graph. We're hoping to include some use cases, future work, and contact information. The resources page shows it's a bibliography of the different CSI documents and resources. So it describes where you can find the R package, where real-time data is available, user's guide is available. The user guide is also available in the back of the report. Published data, publications, and partners. So our next steps and future plans, we want to know how, when, and where can the CSI contribute to drought monitoring and resource management. So what we're looking to do in the future is try to find some case studies so that we can analyze drought, salinity, and ecological linkages. We want to identify critical thresholds and decision points for use in the Coastal Salinity Index and evaluate the use for resource and drought management. So that was the quick overview of the Coastal Salinity Index. Here's a link to the real-time CSI webpage, the current one. That's going to be the 17 gauges in the South Atlantic Water Science Center. The new page should be up at the end of next week, and then also where the R package is located on GitHub. My contact information. So I'd invite anyone to please explore the current website and the new website when it comes out, and feel free to contact me with any questions. Thank you.
Awesome. Thank you so much, Matt. That's super interesting. And we'll definitely stay in touch, Matt, and I'll get when the new link goes live to the expanded version of this, I'll make sure to send it around to everyone that was on this invite. So what turning it over to the group who's been listening here, what questions do you have for Matt? Feel free to unmute yourself or ask in the chat. Well, I'll read one from the chat here. So someone asked, similar to the question asked of Scott, is the CSI amenable to having the user change the data source connection of the package to their internal database? So if you wanted to use that R package for a different data stream, could you do that?
Right. Yeah. The R package currently isn't set up to. It's set up to process the data, but of course, all the heavy lifting to get it to be web-based and that someone would have to incorporate that. But yeah, the scripts themselves should be readily available to process data and calculate for the given input data set. And it describes what the data set should look like.
Okay, got it. And Matt, are you comfortable sharing these slides or some version of these slides with the group?
Yep. Similarly to what Scott said, I'll double check to make sure that it's shareable, and then I'll pass that along to you, Dan.
Okay. Great. Other questions for Matt? Well, I have a question. You mentioned towards the end some case studies or use cases that are kind of in the next steps for you all. I'm curious, do you have your eye on something in particular for a use case, like for harmful algal blooms or oyster impacts, or is there anything you're just that your gut tells you to look for? What are you guys pursuing in terms of finding use cases?
Yeah, so that's exactly some of the things we've been looking at and trying to find cooperators to do. Specifically the oyster stuff, we have a colleague who's interested in oysters, and we're going to try to reach out to see if we can use the Coastal Salinity Index to help with the management of oysters. We've had some local folks in South Carolina who've used it for crab abundances. So they've done a little bit of research with that and are interested in applying it to the availability of fish, finfish, and some other fish types. So yeah, those are the kind of things we're looking for. We're also down the road potentially use it for something like a salinity alert system. See if we can improve on something just over, whether or not the salinity is rising. See if it helps in a predictive capacity potentially. So those are some of the things we've thought about, but just haven't managed to develop those projects just yet.
Okay, great, thanks. So another question from the chat: if the historical data distribution is used to develop the CSI, is there a minimum number of years needed? And what is the impact of a different number of years, for example, a site with 10 years versus 20 years of data?
Right, and that's a very interesting question, and one that we're kind of stuck on currently. We have some folks who are interested in us putting gauges on the web, you know, with shorter periods of record, and we don't know, you know, for the standardized precipitation index, they want 30 years of record for precipitation. Of course, salinity doesn't usually have that long a period of record. When we developed it for the 2019 investigations, to keep a manageable size of gauges, we tried to focus on about 18 years. That was our sweet spot for that project. We could certainly do a little bit less than that, but the question is, yeah, is it meaningful if you only have 5 years of data? You know, it's meaningful for that period of record, but the longer the period of data, the better. And that's currently some of the investigations that we're doing. I've got a gauge with a record of 56 years. I'm going to do some analysis on it and say, what happens if I only have 40 years or 30 years or 10 years? What does it look like? And see how the CSI might change for those last 10 years. That's a great question, something that we're looking into.
Good, thanks. Well, we are almost at 3 o'clock here, so I'm going to call it, but I just want to say thanks again so much to you, Matt, and to you, Scott, for teaching us today. We really appreciated this, and we'll be in touch about sharing the slides with this group. To Water Council members and alternates, I'll send an email out in the next couple days about a date coming up mid-October that we're going to meet to discuss our 2021 work plan. So be on the lookout for that. So thanks again, everyone, and we will be in touch soon. Have a good afternoon.
Thank you.